Hello, everyone. Welcome back to my practice exam series. If this is your first time here, I'm Robbie Richmond. I'm one of the TAs for Dr. Outlaw this semester, and I usually make these videos right before the exam in purpose to kind of show what I did to succeed in these classes and get A's on all my exams when I took this class. There is a lot of strategies and a lot of things that, is stuff that is not as intuitive as you think, and in hopes of just spreading out information and making sure y'all feel prepared for this exam, I make these videos. Now, if I say something throughout the video that you're still kind of confused on or don't really understand the explanation, please email me or come to my office hours, which are listed in the syllabus. Um, and yeah, I think by now we got through the first exam and we kind of understand the entire process of how this goes. You'll be given an exam packet with first name, last name, signature, student ID number. Just put that information down and check your section in the box there. You'll be given a sheet of multiple choice questions. These won't be graded. The only thing that will be graded is this answer sheet with the free response questions attached to it. In addition, you'll also be provided an exam information sheet which can be found on Canvas and a periodic table. Before we dive into just breaking down this exam, I want to remind everyone to look at where you need to be for your exam. I don't know if this has happened in the last exam, but if you go to the wrong exam location and take your exam for the wrong section, that's just going to be a huge headache for you and Dr. Outlaw, and the time it takes for Dr. Outlaw to grade your exam will be significantly longer than everyone else. So please do your due diligence. Please look at that. And yeah. All right. So before I even start going over questions, this is a strategy that I usually use for any exam, regardless if it's chemistry or not. Go and find a blank sheet of paper within the exam and write down some things that you remember off the top of your head about this exam. For this exam, I would heavily recommend writing down your overall periodic trends and the just very important key characteristics of the periodic table. So, the major ones that we went over is effective nuclear charge. That increases from left to right. We also went over both atomic radius and first ionization energy. So atomic radius increases from fluorine to francium, which is going to be in pink. Then in blue, I'm going to write the ionization energy trend, which goes from francium to fluorine. Cool. On top of that, I would also write down some information about ions. So group 1, that's usually going to be a positive 1. This is going to be a positive 2, negative 3, negative 2, negative 1. And I'd also kind of underline zinc, cadmium, silver, and write down those respective charges. So these are all your charges that are going to be fixed. Now, if you want, I would also just write down, this is S, this is D, all of these are P, and I doubt you're gonna be asked about this, but the lanthanoids and acetinoids, those are F block elements. Cool. Oh, I did forget to say about just things before you even get to the exam room. Make sure you have a scientific calculator. That was what I was forgetting. Okay. So if you watched my previous video, I said to start with the free response questions. That still holds true, in my opinion, for this exam as well. Just make sure that, if you start getting stuck on something like question 21 that There's a lot of organic chemistry nomenclature in there that might kind of scare you, and you take a lot of time for that. Skip it. You can come back to it. I think just even seeing the question and letting your brain to think about it throughout the entire exam or let it reflect on the entire exam, you might go through a multiple choice question that kind of jogs your memory on how to solve that specific problem. So always start with the free response questions, but if you start getting stuck, don't stay on it for 20 minutes because you will run out of time. Okay, cool. Starting with question 18, circle the element that fits the criteria listed to the left, lowest effective nuclear charge. So we have potassium, germanium, arsenic, selenium, and bromine. Anything that's going to be the leftmost, aka group 1, that's going to have the lowest effective nuclear charge. I see potassium, that's a group 1 element. There's nothing more left than that. So potassium is going to be our lowest effective nuclear charge. Now if we look, just to solidify this concept, what the highest effective nuclear charge is, I would say bromine. Is there anything in noble gas? There's not. So bromine would be our element with the highest effective nuclear charge. Remember, left to right. Then we're asked for largest first ionization energy. I'm actually going to take a little screenshot of these guys. Let's go up here. Alrighty. So we're looking for largest first ionization energy. That is going to be our blue arrow. And you can also label it. It's whatever you want to write on your exam. But our ionization energy trend is going to be our blue. I see oxygen. That is the closest to our tip of the arrow. That's going to be our answer. Then we have most valence electrons. This isn't a periodic trend, but this is a concept that we did cover in class. Valence electrons are any electrons within the highest energy level. So I think I should have added these. This is energy 1, 2, 3, not 3, 4, 5, 6, and 7. And that represents the principal quantum number. So any electron within the highest principal quantum number in a given electron configuration will be the valence electrons. So in this instance, I'm probably just going to look for anything that is a noble gas configuration because it has all the, let's say, for instance, if this was a period 3 element or a period, let's say period 2 element, this would have the 2s block electrons, 2s2, and it would have the 6 2p electrons, having a total of 8. And since all your answer choices are within the second period, I see neon, that's the noble gas there. So that has 8 electrons, valence electrons. Carbon, actually, I'm not going to break that down. It's going to take a little too much time. Cool. Question 19. Circle all the atoms and ions that are isoelectronic to iodine with a negative charge. Make sure to read your question fully because when I was preparing for this video, I did not see the little negative charge on iodine. I was very confused. So just double read your answers, or not your answers, your question. So this is ground state iodine right here in pink. If we added another electron, it would be the electron configuration of xenon. So our goal for here is to find which element and or ions have the same electron configuration as xenon. So I see Te2, -2, Te is right here. If I added 2 electrons, that would have the same electron configuration, aka isoelectronic. Iodine, that's ground state iodine. Nope. Bromine, if I added 1 more electron to bromine, that would be the krypton electron configuration. Nope. Then CCM plus. CCM is right over here on the left in row 6. If we lose an electron, it would have the same isoelectronic configuration. And then SR plus 2, that is right here. If we lost 2 electrons, that would be a krypton electron configuration. So that is not what we're looking for. So Te -2 and CS plus, that is our isoelectronic to iodine negative. Cool. A particular chloride ion has a charge of -1 and a mass number of 37. Let's write that information down. Cool. And we're just given protons, neutrons, electrons, and are expected to fill that out. Now, if you look at your periodic table, the identity of an element is determined by how many protons there are. I see that 17 above chlorine, so that's going to have 17 protons. And to get a mass number, we add our protons and neutrons to get that 37. So to find the amount of neutrons, 37 minus 17 will give us neutrons, and that would be 20. Then, this is pretty counterintuitive. We would have 18 electrons. And the reasoning is because electrons are negative. So if we have one more negative than positive, it would be a -1 charge. Some people are thinking of it in the opposite way, where they would write 16 electrons because that's one less. That would be a positive charge because there's one more proton than electron. Since there's a -1 charge, we would need more electrons than protons. Cool. Question 21. In 2024, scientists first detected the 13-atom molecule 2-methoxyethanol, that's the formula given there, in the Cat's Paw Nebula. A scientist has a sample of 2-methoxyethanol and determines that the sample contains 5.2 times 10 to the 28 hydrogen atoms. How many moles of 2-methoxyethanol are in a sample? Cool. So breaking down this question, I know this is really scary, 2-methoxyethanol. If you go into organic chemistry, you'll figure out what this means. But going back to Gen Chem, this is just a molecule comprised of many things, which the formula is given here. Our goal is to figure out how many moles that we have, and we're given how many hydrogen atoms we have. So, what should we start with? Obviously, the only thing that has a number, 5.2 times 10 to the 28 H atoms. Now, how can we convert this to something where we can get to moles? You can't really directly convert it to moles exactly, but we have an intermediate way. Look at this formula. It has a lot of hydrogens in it, right? So, if we figure out that this is 3 plus 2 plus 2 plus 1, that's 8 hydrogens in 2-methoxyethanol. For every 8 hydrogens we have in our sample, that is going to be equivalent to 1 molecule of 2-methoxyethanol. So, for every 8 hydrogen atoms, that is going to equal 1 molecule of that compound. Cool. And make sure to write that down. I'm just going to be lazy for now. Now, we have everything in terms of molecules. How can we convert that to moles? Obviously, Avogadro's number. So, put molecules on the bottom because we're trying to cancel out molecules and we're trying to convert it to moles. Definition of Avogadro's number. 1 mole of anything doesn't have to be molecules, it can be anything, is 6.022 times 10 to the 23rd. And if you forget that, it's in your exam information sheet. Cool. Now I would stop here and look at all of our units and make sure we're canceling out to see if we're close to our answer or have our answer. H atoms, that cancels out. Molecules, that cancels out. And we're left with moles of 2-methoxyethanol. That's what we're looking for. Cool. Now, I say this in every office hour that I do. Shameless plug there. Take all of the numerators and multiply them by each other. Then divide them by the product of all your denominators. So what that's going to look like in your calculator, I don't have a view of it. Unfortunately, I do want to figure out how to do that. But you're just going to take 5.2 times 10 to the 28th times 1 times 1, hit enter into the calculator. Then you're going to hit divide and take 8 times Avogadro's number and make sure that this is all in parentheses. Because if you don't put it in parentheses, you are not going to get the right answer. So I get 10,793.7 goes on for a hot while. Goes on for a while. Moles of 2-methoxyethanol. Cool. We're not done yet. Remember, we have to round everything for sig figs. So let's break that down. 5.2 times 10 to the 28th H atoms, that is measured 2 sig figs. Now this, 8 H atoms for 1 molecule of 2-methoxyethanol, that is going to be infinite sig figs. And the reasoning is, by definition, we're going to have 8 hydrogens within 2-methoxyethanol per that formula. Every single time, there's no uncertainty there. Now, for Avogadro's number, that is 4 sig figs right there. And by the rules of multiplication and division, we would round our answer to 2 sig figs. So I would get 11,000, 11,000 moles of 2-methoxyethanol. Last thing I would do, this is definitely not required of you, but I would recommend you do this just so it makes Dr. Outlaw's life a little bit easier. Just box your answer. Cool. Going on. Complete the orbital energy diagram for what element are we doing this for? Silicon. Alrighty. Let's find silicon on our periodic table and let's talk about how to read the periodic table. So silicon is going to be this guy right here. When we're reading the periodic table, read it like a paragraph. We start with our first row and we read from left to right. So we read from 1s2, that's completely full, to 2s2, that's completely full, to 2p6, that's completely full, to 3s2, that's completely full. Now here, we only have 2 electrons to get to a neutral charge of silicon. So instead of 3p6, we would put 3p2. Cool. I'm going to copy this. And I'm going to move back to our free response questions. Write down right here. All right. Now, translating this to the orbital energy diagram, remember, this little line represents the orbitals, and the up and down arrow represents the electrons. In each orbital, there can only be 2 electrons. So, if I have a 2s2, there's 2 electrons in one orbital, 2s. 3p, there would be 3 orbitals. Well, Then S, that would only have one orbital. Then P, that would also still have 3 orbitals. And you may be asking, how did I determine this? Quantum numbers. That thing doesn't leave you. If we have a p orbital, that L value is going to be 1, and the ML value would be -1, 0, and +1, meaning that there's 3 orbitals. And each orbital fits 2 electrons. So let's write down that information for the electrons, up, down. Everything up until 3p would be completely full. Now, if I wrote this down, this would be incorrect because it violates Hund's rule. Hund's rule states that we need to fill each orbital with at least 1 electron before we pair them up. So, since we only have 2 electrons, I would write 2 up arrows in 2 different orbitals in the 3p level. Now, question 22b, how many unpaired electrons are there in the orbital energy diagram of silicon? 2, because we have those 2 up arrows that doesn't have a complementary down arrow. Alrighty, last free response question. This is just nomenclature. So just to recap, molecular compounds and ionic compounds follow different nomenclature rules. Molecular compounds are, in my opinion, the easier of the two. Basically, all you do is write the identity of the first element with the prefix of how many of that element you have. So mono, that means 1, di, 2, tri, 3, tetra, 4, so on and so forth. The last element, you would still put that prefix, and then you would put a suffix of IDE. So, for question A, although this does look like sulfate, this doesn't have a -2 charge, so it's a molecular compound. It would be simply sulfur tetraoxide. Or, sorry, not tetraoxide, tetroxide. I doubt that Dr. Outlaw is going to be very stringent on this, but to be very precise, tetroxide is a little bit more correct than tetraoxide. My pencil's not cooperating with me, sorry. Cool. Now you may be asking, why did I not put monosulfur? For the first element, you do not have to put mono. That is redundant. If it was S2O4, I would have to put a prefix to denote that there's 2, but since there's only 1 for that first element, we just leave it be. Alright, B, MgS, that is magnesium and sulfur, a metal and a nonmetal, that's an ionic compound. Ionic compound rules is basically you write down the identity of the element or polyatomic ion. You don't put any prefixes, you just write down the identity of it. Now, the only weird rule about this is when we have transition metals that have variable charges, stuff like manganese, that can have +1, +2, +3, and +4 charges. So what do? We put those in parentheses and write a numeral denoting that's a positive charge of how much. But for magnesium, that's a group 2 element and something that we wrote down in our periodic table. That has a +2 charge. So it's always going to be +2. We don't have to write down that Roman numeral. So it would just be magnesium sulfide. Okay. C. We have chromium and we have nitrogen. So I'm not going to write down... Ooh. think that's how you spell that. Yeah, nitride. Now let's check if this is one of our transition metals that has variable charges. Let's look at our little periodic table, which we noted that zinc, cadmium, and silver have fixed charges. Everything else doesn't. And also note that nitrogen has always a -3 charge. So to figure out what Roman numeral we need to put down, if we have two nitrogens that have a -3 charge, overall that's going to be a -6 charge. And since we're trying to balance out the charges for a net 0 charge, chromium needs to be a +2 charge. +2 times 3 would be 6. 6 minus 6, that is 0. So it would be chromium 2 nitride. Alrighty. K2SO4, I see a polyatomic ion, that's ionic. Nomenclature rules that we're going to be using. So simply potassium sulfate. Now potassium is always a fixed charge, that's a group 1 element, so we don't have to put down the Roman numerals. Okay, so for these first 4 questions, I do want to remind you, you don't have to be perfect in the spelling. Like chromium, if I forgot the H there, I believe Dr. Alla would be lenient and understanding of that. However, if I put sulfite instead of sulfate, those mean 2 different things, and she would mark that wrong. So for those polyatomic ions, make sure you're spelling them right. Alrighty, going on to converting the nomenclature to a formula. Copper 2 oxide. Oxygen always has a -2 charge based on what we covered in class, and copper, that's a +2 charge. We only need one of each to cancel out the charges for a net 0. Then calcium phosphite. Calcium is a +2 charge based off of the periodic table, and phosphite always has a polyatomic ion of this. To balance the charges out, you would need 3 calcium, put parentheses around phosphite, and we would need 2 of those. To double check, we can just do the math again. +2 times 3, -3, -3 times 2, that's 6, -6, that's a net of 0. We're good. Reminder, please put parentheses around the polyatomic ion if you want to put multiple of that. Do not put P2O6. That is something completely different. Cool. Tetranitrogen decahydride. This is going to be a molecular compound. So we just put 4 nitrogens and 10 hydrogens. Cool. Selenium, Se, that's going to have a -2 charge, and figure that out by looking at our periodic table. That's going to be a group 6 element, so that always has a -2 charge in its anion form. And then we're given that information that manganese has a +4 charge. To balance that out, we would just need 2 seleniums. Cool. All right, now we just solved all of our free response questions. Let's dive into the multiple choice. What is the molar mass of the compound of this? So to figure that out, we just take the molar masses of each element and multiply it by how much we have in that compound. So what do I mean by that? We have 1 magnesium. We have 4 hydrogens because it's multiplied by 2, because it's all around in parentheses. 2 phosphorus and 8 oxygens. Then we would just times it by its molar mass. Add them all up, and that should be the molar mass of the entire compound. Now, Me putting that into my calculator would take way too much time and we could cover all the other things more in depth. So I'm just going to say that the answer choice is D. But if you want to write down all the information, go for it. Alrighty. Question 2. A compound is 83.65% carbon by mass and the remainder compound is hydrogen, meaning hydrogen, that's going to be 16.35% of that compound. What is the possible molecular formula for this compound? So there is the way that we covered in class, and then the way that Dr. Outlaw did not cover in class that works for the multiple choice questions. I don't recommend doing the second option, but I'll show it to you just in case, you panic and you blank and you forget how to do this. But let's just go over how we normally solve this. First, we assume 100 grams of the compound. So if it's 83.65% carbon by mass, it would be 83.65 grams of carbon. Then for hydrogen, it would be 16.35 grams of hydrogen. Then we find out how much moles that is. 12.01 grams of carbon, that's 1 mole. Then 1.008 grams of hydrogen is 1 mole of hydrogen. Get that? I get 6.96 goes on for a while, and 16.2. Next step is to divide by the lowest amount of moles to get a ratio of each element. So in this case, hydrogen, whoa. Sorry, these should be flipped. Sorry about that. So hydrogen would be the least amount of moles for that. So we divide everything by 6.96. And we will get a ratio of carbons to hydrogens, aka empirical formula. So 6.96 divided by 6.96, that's going to be 1 hydrogen. Then for carbon, 16.22 divided by 6.96, that's going to be 2.33 carbon. There's an issue here. We cannot write C subscript 2.33H. To solve that, we will just have to, oh my god, I'm sorry. What am I doing? I am like mixing up my numbers and everything. Sorry about that. These are the right numbers. I don't know why I decided to flip everything. That seems more right. Same steps follow, just don't flip it like I did. All right. To solve this issue, we wouldn't write CH2.335. We would just multiply everything by a factor. In this case, we would multiply everything by 3. So in reality, we would have C3H2.33 times 3. That would be 7. Okay, let's see if we have an answer choice of that. We do not. Now, do not panic. Do not worry. Remember, this is an empirical formula. The question is asking about molecular formula for this compound. And if you remember the difference between a molecular and an empirical formula, the empirical formula is the lowest ratio. So if it still has that 3:7 ratio, that is still the same distribution of 83.65 carbon by mass and 16.35% hydrogen by mass. So our next step would be 6 carbons and 14 hydrogens, and then going even more than that. I doubt that we will need to do that. That would be 21. Okay. And I see answer choice B, 6 carbons, 14 hydrogens. That would be a possible molecular formula for this compound. Alrighty. That is the proven way to solve this. The less intuitive way to solve this, and this only works for multiple choice questions, is to look at the molecular weight of each answer choice and multiply it by how much you have and get a ratio and percentage based off of that. So what do I mean by that? 6 times 12.01, that is 72.06, plus 1.008 times 14. This would be a molecular weight of 86.172. And if we have 6 carbons with a weight of 12.01 of each, that would be 72.06 divided by the entire molecular weight times 100%. That would give us, drum roll please, 0.83 or 83.6%. That is basically what the problem said. That's a way to check your answer, and if you're kind of forgetting how to do this, that's a way to kind of engineer it backwards. Do I recommend doing it? No, because that takes a lot of time. However, if it works, it works. Alrighty. Question 3. This is exam 1 stuff. I know that this exam mostly covers chapters 4 and 5. However, you cannot just forget chapters 1 through 3 because those are essential for the rest of this class and the rest of the time you're doing chemistry at UNC Charlotte. So, this is simply just an adding sig fig question. And the rule for adding sig figs is we will round to the leftmost place of digit. So, how do I do this? I go and add everything and line all the numbers up. So this would be the thousandths place. This would be the hundredths, tenths, ones, and tenths. Now I would denote where the last significant digit is. For 3000, that this is the last place. And then for 184.4, this is the last place. The leftmost is where we round it to. So although if you put it in your calculator, you would get 3,184.4 per the not multiplication, the addition and subtraction sig fig rules, you would round it to the thousandths place, which would simply just be 3,000. Cool. Alrighty, potassium chloride. How many grams of potassium chloride are in 46.2 moles of potassium chloride? Potassium chloride, K, that has a positive charge. Cl has a negative charge, so our ionic compound would just be simply KCl. To figure out the molecular weight of this, we would just add the molecular weights of potassium and chlorine. So 39.1 plus 35.45, I get a molecular weight of 74.55 grams per mole. Grams per mole. Since we have 46.2 moles of potassium, I put it on my numerator, moles cancel out, and we're left with grams. So it'd simply just be 74.55 times 46.2. I get 3,000 444.21. If we're looking at sig fig rules, we were rounded to 3 sig figs, which is answer choice A. Cool. Which ionic compounds form between Ag and nitrate ions? Alrighty, Ag and nitrate. Nitrate is NO3 negative, and Ag, let's look at this. Huh, that's cool. I wrote that down. That is a fixed charge, that is silver, and that always has a +2 charge. Hint, hint, nudge, nudge. Please write that down on your exam information sheet and periodic table, because without it, you would have no idea how to solve this question. So, nitrate has a -2 charge. What am I doing? If our goal for an ionic formula is to to get a neutral atom and balance out all the charges, we would have 1 silver and 1 nitrate. Wait, this feels wrong. Oh. I'm so sorry, folks. I was right about nitrate being a -1 charge. Silver is a plus charge. Nitrate's negative charge. Let me triple check that actually. Yeah. Okay. Silver is a +1 charge, and nitrate's a -1 charge. That is my bad. Alrighty. Determine the mass percentage of oxygen in iron 2 hydroxide. Hydroxide has a negative charge. Iron 2 has a +2 charge. So the actual formula would be this. And we're looking for mass percent of oxygen. So I would just get the entire molecular weight of iron 2 hydroxide. That would be, let's see, iron 55.85 plus 32 plus 2.016. I get 89.866 for our molecular weight. And then getting the mass percent of oxygen, we just take our 32, all that times 100%, and that would be the mass percentage of oxygen within this compound. Just to reiterate, this is the molecular weight of iron 2 hydroxide, and this right here is the molecular weight of those 2 oxygens. Cool? All right. That divided by that times 100. I get 35.608%, which if we're looking at sig figs, that would round to 4 sig figs. Answer choice D. Cool. Number 7. Consider a chlorine atom. Identify the most likely subshell from which an electron would be removed in the process of ionization. Alrighty. Chlorine atom. So, if we're looking at chlorine, this is within the p block, specifically the 3p block, that last electron. If we're doing ionization, we are removing an electron that's going to be usually at the highest energy level. So, simply, we would be removing an electron from the 3p. Cool. Which of the following orbitals cannot exist? Oh my god, guys, look at that. Exam 1 question. So, how do I solve this? Remember, n can equal 0 to infinity. L can equal from 0 to n minus 1. And I think that's all the information we need to solve this. So let's look at answer choice A. N is 2, and L for p orbital, that equals 1. That follows that n minus 1 rule, so answer choice A can't exist. Answer choice B, n equals 3, and for L, that equals 2. That's possible. That fits the n minus 1 rule. Cool. 4D, n equals 3. Whoa, n equals 4. And L, that's a d orbital. That correlates to an L value of 2. Follows that n minus 1 rule. N equals 1. L, that also equals 1. That violates the n minus 1 rule. Our only value of L that's possible for n equals 1 is 0. So this is our answer choice, but let's double check with answer choice E. N equals 12, and for P, that's an L value of 1. That fits within our n minus 1 rule. Cool. And if you're still kind of confused on that, please refer to my exam 1 video just linked onto my YouTube channel. I went over a table that you can 100% just also add to your exam information sheet that goes over all the critical information about the quantum numbers that we covered for exam 1. All right, question 9. Which pair of elements do you expect to be most similar in terms of chemical reactivity? When we're talking about something that's similar in a chemical sense, we're thinking of something that's within the same group. So, take all of these answer choices. I'm going to just save them and then go up here. So basically, they fall within the same column. That's what we're looking for. Nitrogen and carbon, they do not fall in the same column. Titanium and gallium, those are transition metals. Transition metals usually do not have the same property. They are very diverse, even within the same column. Sodium and magnesium, that is an alkali and alkali earth metal. That's not what we're looking for. Magnesium and calcium, I'm going to circle these two because they are within the same column in groups 1 or in group 2. So that means they have very similar physical and chemical properties. So that's our answer choice, but let's look at answer choice E to just process of elimination and make sure that we got the right answer and came to the right conclusion. Argon and bromine. Argon's a noble gas and bromine's a halogen. They would not have very similar chemical properties to each other. Answer choice D. A chemist isolated a sample of a certain element and determined a few of its properties. The element is larger than nitrogen, smaller than strontium, and easily ionized to form a cation. What is the probable identity of this element? Okay, a lot to unpack here. Let's take this and start looking at our periodic table one more time. So, let's find a new color for this. Purple. All right. So, it's larger than nitrogen. And remember, that pink arrow going from F to FR, that is our increasing atomic radius trend. So it should be anything going from here to here. But it's also smaller than strontium, which is SR. So it can't be cesium, it can't be francium. And it's easily ionized to form a cation. So we're talking about things that kind of fall. This is a lot in this area, but something kind of like within this realm. So let's see. Anything that falls within the periodic table in that realm. Oxygen's kind of out of that. Rubidium is also kind of lower down. Sulfur further than nitrogen. Selenium is outside of that range. Calcium, let's double check. Yep, it would be smaller. It would be larger than strontium, but smaller than nitrogen. Wait, opposite. Smaller than strontium, larger than nitrogen. Kind of confused that there. Sorry about that. So answer choice E would be your answer. Which of the following statements regarding magnesium and lithium are true? Cool. Let's go by each answer choice. 1 mole of magnesium has more protons than 1 mole of lithium. Magnesium, let's see how much. So magnesium has 12 protons in just 1 magnesium atom, and lithium only has 3. If we're comparing mole by mole, magnesium would have 1 or more protons. So answer choice A is right. Let's go through all the other ones. 1 gram of lithium consists of fewer atoms than 1 gram of magnesium. I would actually argue the opposite because the molecular weight of lithium is significantly less. 1 mole of lithium has the same mass as 1 mole of magnesium. Nope, they have different molecular weights. Answer choice D, 1 mole of lithium consists of fewer atoms than 1 mole of magnesium. A mole means the same thing. Avogadro's number, they would have the same amount of atoms. And then that's the same reason why answer choice E is also wrong. Cool. 12. How many valence electrons are in the Pb atom? I did brush over this. Remember, valence electrons are... God, this is a lot happening in this. Let's try to erase. Valence electrons are basically any electron within the highest energy level. So for Pb, which is located here, we are looking for this row. So cesium, 2, 3, 4. This would have 4 valence electrons within that highest energy level. It would have a 6s in 6s2, 6p2 configuration for those last 2 ones. So it would have 4, which actually is not here. So answer choice E. Alrighty. What is the ground state electron configuration for Rb ion? Alrighty. So remember, if we're ionizing an ion, it comes from the God, what am I saying? It comes from the higher energy level. So rubidium, let's find that bad boy. Right here. So if we're ionizing and we're losing 1 electron, it comes from that 5s1 level and goes to the 4p6. So all I'm looking for is everything filled up to 4p6, and that answer choice would be answer choice E. Cool. 14. Which of the following electron configurations belongs to an atom that is a transition metal? Remember, we don't have to look at the identity of each of these elements. We can look at simply this D block right here. The D block is comprised of mostly transition metals. So if I see anything that ends with a D in the electron configuration. Donuts to dollars, that's going to be our answer choice. Answer choice B. Cool. The following graph shows successive ionization energies from a certain third period element. To which element could this graph belong? Alrighty. Remember, this is normal, like just normal charge. It lost one electron and it cost that much energy. Then it lost a second one, cost that much energy. Now, look at the difference between ionization energy 2 and ionization energy 3. That is a very significant jump in kilojoules per mole. That indicates that whenever we lost that second electron, that was our noble gas configuration. And to deviate and lose another electron from that noble gas configuration, we would spend a significantly more energy. So you see that jump. So basically, all this is saying is whatever is 2 away from neon, because we're looking at period 3 elements, and that would be magnesium. Loses 1 electron, ionization energy 1, then loses that second one. We have that neon configuration, that's a noble gas. Then if we wanted to remove a third electron, that would be a significant difference in energy and require a lot more energy. Hence the jump between ionization energy 2 and ionization energy 3. So our answer would be magnesium. Cool. Rank the following radii from smallest to largest. We have Ba2, cesium, and iodine. All right. Let's clear some information on this periodic table because it's starting to get messy again. Okay. Cs plus, Ba2, I negative. I'm just going to write that down. Okay. For this one, remember, our trend for radius is that pink arrow going from fluorine to francium. So anything near the lower left generally should be larger. However, we are dealing with a lot of ions, and in this case it looks like might be a possibility of isoelectronics happening here, isoelectronic series. So if we have ground state barium and we lose 2, we would have electron configuration as xenon. If we have cesium and we lose 1 electron, that would also have a ground state or electron configuration as xenon. Then for iodine, if we gain 1 electron, that would have the electron configuration of xenon. So how do we determine which one is larger when which one is smaller? Remember our effective nuclear charge trend. That trend basically says that the electrons from the outer edge, the valence electrons, will feel more charge from the nucleus if the effective nuclear charge is large. So you see how this atomic radius trend goes from the right to the left? That kind of is opposite to effective nuclear charge. So we can say that from an effective nuclear charge standpoint, if we have a higher effective nuclear charge, generally it's going to be a smaller radii atom. And you can think about it like the nucleus is more effective at being nucleus and being positive, so it's sucking in those electrons. So we just look at our effective nuclear charge trend and extrapolate it for radius. So I see iodine, that's going to be the highest effective nuclear charge. Then it's going to be barium, then cesium. So our smallest would be... Hold on. Scratch what I just said. Yeah, okay. Sorry, I'm getting myself confused here. So, disregard what I just said. Barium has 56 protons, cesium has 55 protons, and iodine has 53 protons. When we calculate effective nuclear charge, it is basically protons minus the core electrons. If we have the same amount of core electrons for xenon because they're all isoelectronic, the only differentiating factor is how many protons we have. So if you have more protons, that's a higher effective nuclear charge. That same trend is true. So effective nuclear charge goes from left to right, and just because of how effective nuclear charge is and what it's calculating how effective the nucleus is sucking in our electrons from the outside. So for this case, if we have the only differentiating factor is protons, more protons would mean that the nucleus is sucking in those electrons from the outside more efficiently. So our smallest would be barium because it has the most amount of protons. And iodine would be our largest because it has the least amount of protons, resulting in a smaller effective nuclear charge. If you have any issues with how I phrased it, please send me an email and I can further explain how this works. Alrighty. Question 17. Which of the following statements is false? Alright. When effective nuclear charge is high, there is a large difference between the number of protons and the number of core electrons. Kind of what we just talked about. Remember, effective nuclear charge is protons minus core electrons, which we say is psi. So, if the difference between this is large, effective nuclear charge is going to be high. So that's true. Statement 2, when effective nuclear charge is high, the radius of an atom will become smaller. That's also what we kind of just touched on in question 16. Look how the effective nuclear charge increases from left to right. However, the atomic radius decreases. So it basically has an inverse relationship. So that is true. Statement number 3. When effective nuclear charge is high, the valence electron experiences little attraction to the nucleus. That is not true. And the reasoning is, effective nuclear charge is saying, or given a quantifiable amount of how strong the nucleus is and how it's affecting the attraction of the electrons in the valence electrons. So if effective nuclear charge is high, it's pretty effective at sucking in those electrons towards the nucleus and feeling the attraction. So I would say statement 3 is the only one that's false. All right. And that wraps up all of the questions for this practice exam video. If you have any questions regarding any of my explanations, please come to my office hours or talk to me after class or talk to me via email. I will do my best to respond to your emails. Please don't expect me to respond during the weekends, but during the weekdays, I try my best to respond within the day, and if not, within 2 days. Thank you.